Let's talk about quadratic equations and quadratic equations that can be written from things that don't initially look like they're quadratic but can be rewritten in quadratic form. In order to talk about these, we're going to first discuss factoring in the zero product property. Then we will be discussing the square root property, then the quadratic formula, and then finally equations that can be rewritten in quadratic form. You are encouraged to use the timestamps on this video if there's a particular topic that you want to get to right away. So first of all, what is a quadratic equation? A quadratic equation is essentially anything where the highest power is an x squared, perhaps multiplied by something, perhaps not, and perhaps with lower powers such as something with plane x or something that is a constant added on to it. The zero product property is a fancy way of saying an idea that you already know. Because if I say 7 times something is equal to 0, what does that something have to be? 0. That's all it's saying. So if I have x minus 7 times x plus 3 equal to 0, what has to be equal to 0? Either x minus 7 is 0 or x plus 3 is 0. That's really what we're using whenever we say the zero product property, is this fundamental idea that the only way to get 0 is if one of the things being multiplied is 0. Now, we mentioned last time domain, and something that we might want to think about, because we want to think about this with all of our types of functions, is what would be the domain of this function. Are there any numbers that I'm not allowed to plug into something squared? No, there are not. So for a quadratic function, we actually also have all real numbers as the domain. This is, again, not something that's super emphasized in this part of the course yet, but we will be emphasizing it very shortly. So something to think about is that all linear functions, all real numbers are allowed to be plugged in. All quadratic functions, all real numbers are allowed to be plugged in. So let's use the zero product property in action. So let's say you're given a quadratic function in this factored form. We'll go over how to transform between factored and unfactored form here shortly, but let's say this is the equation that you are given, and you're asked to find the x-intercepts and the y-intercepts. Well, if it's an x-intercept, how do I find those again? I plug in y is 0. So if the equation is y is equal to x plus 3 times 2x minus 5, remember these parentheses are really being multiplied in between, that's what they're indicating. I replace y with 0 to get 0 is equal to x plus 3 times 2x minus 5. And then the zero product property allows me to say that if 0 is equal to something times something else, then either x plus 3 is equal to 0 or 2x minus 5 is equal to 0. So we always break up factored form into these two mini equations. Then we just solve them using our linear equation techniques. So if x plus 3 is equal to 0, the only thing I have to undo is adding 3 by subtracting 3. 3 minus 3 makes 0, so x is equal to 0 minus 3 is negative 3. For the other one, we do the same thing. So first we undo any addition or subtraction. So the way I undo subtracting 5 is adding 5 to both sides. So 2x is equal to 5. Then I want to undo multiplying by 2, so I divide by 2 on both sides. So x is equal to 5 halves. And what I really just found out is that my x-intercepts exist at the points negative 3, 0, since I just found this by plugging in 0 for y, and negative 5 halves, 0. Those are our x-intercepts. For the y-intercepts, these actually tend to be usually a little bit less arithmetic, because for a y-intercept you plug in x is equal to 0. So y is equal to x plus 3 times 2x minus 5 normally. So y is equal to 0 plus 3 times 2 times 0 minus 5 when we're talking about the x-intercept. 0 plus 3 is just 3. 2 times 0 is 0 minus 5 leaves me with negative 5. So we end up with y is equal to negative 15. So our y-intercept is at the point 0, negative 15, because I just found it by plugging in 0 for x. Now we want to make things look like that nice form we just had so that we can easily find x and y intercepts. If we have some sort of quadratic equation like this, where it's already set equal to 0, the nicest way to solve this is to factor it. If it is just a plain x squared with no leading coefficient, we say this is a special case of factoring. We're going to go over how to factor this when the leading coefficient is something other than 1 momentarily, and that will also work in this case. But this technique is just whenever I have an x squared plus something times x, perhaps plus a constant, equals 0. In order to factor things in this specific form, the question we want to ask ourselves is, what two numbers will equal the constant c but add up to b? We can then rewrite this as two factors. Here there is a small typo on your slides. That should be an x plus 2 right there. I'll make note of that in the version that is on Canvas, but just so that you see that here. So if, for example, we knew that the numbers that were to multiply to c and add to b were 1 and 2, then we would have the factors of x plus 1 and x plus 2. Then we could solve using the zero product property. So let's actually see that in action. So let's identify what is b and what is c here. So c in this case is -6, and b, if I see an x by itself, there is secretly a 1 in front, so b is 1. So we want to ask ourselves, what's going to multiply to -6 but add to 1? In this case, that would be positive 3 and -2, since positive 3 times -2 is equal to -6, and positive 3 plus -2 is equal to 1. If in doubt, just actually start listing out some factors until they work. Since we have figured that out, and this is specifically the case where there is just a 1 in front of the x squared, nothing else, then we can go ahead and factor this into x plus 3, x minus 2, is equal to 0. We really just added a -2, but adding a negative oftentimes is just thought of as subtracting a positive. Now that we have gotten here, this is all set up to just solve with the zero product property. So we split this up into our two mini equations, either x plus 3 is equal to 0, or x minus 2 is equal to 0. Both of these are nice one-step equations, so we undo adding 3 by subtracting 3. X is equal to -3. We undo subtracting 2 by adding 2. X is equal to 2. So when we're talking about our total solutions, x is equal to both -3 and 2. Either of those numbers are going to work. And to be clear, this is a comma just separating the two different solutions. If you were to talk about the literal equation, if this was equal to y and I plugged in y as 0, then those actual points would be -3, 0 and 2, 0. In this case, they just wanted us to solve the equation, not think about the ordered pair on the function though, so you can just list it this way. I want you to go ahead and try this next one yourself. So identify first what is b and what is c, and then go ahead and try to factor him. Welcome back. Let's first identify these components. So in this case, b is the number in front of the regular x, the x without an exponent, so that's just -5. Keep in mind the sign does follow him. And c is -6. Then we want to ask ourselves, what's going to multiply to c but add to b? So if I wasn't sure, I would just start listing out some factors of -6. And if we're going to multiply to a negative, one has to be positive, one has to be negative. So if I was looking at 3 and -2, that doesn't work because that adds to 1. Even if I flip the signs, -3 and +2, that adds to -1. Another factor of -6, however, would be either -6 and +1 or +6 and -1. Since we want to add to a -5, we want to go with -6 and -1, since -6 plus 1 is equal to -5. So this factors into x minus 6 times x plus 1 is equal to 0. And now we're ready to solve these as our two mini equations. So you set up one mini equation as x minus 6 is equal to 0, and the other mini equation is x plus 1 is equal to 0. Since if something times something is 0, one of those two somethings better be 0. Then we just have some one-step equations. So x minus 6 equals 0. The way we undo subtracting 6 is adding 6. -6 plus 6 makes 0, so x is equal to 0 plus 6 is 6. Similarly, the way we undo adding 1 is subtracting 1. 1 minus 1 is 0. 0 minus 1 is -1. So our two solutions are positive 6 and negative 1. Equations that look like this you may have seen in the past specifically as a difference of squares, which is a fine way to approach it. You also can just think of this as a special case of the equations we just looked at. Because here, if I asked you to identify b and c, you would be slightly confused at first because you'd say, well, there is no x by itself. So that means this equation can really be rewritten as x squared plus 0 times x is kind of a place value holder. Minus 9 is 0, because 0 times x is simply 0. That's why it's not written. Now in this way, you see that b is equal to 0 and c is equal to negative 9. So we're trying to multiply to negative 9 and add to 0. And what two numbers would do that? That would be 3 and negative 3. So this can be rewritten as x plus 3 times x minus 3 is equal to 0. Which, if you notice, 3 is just the square root of 9. That's why you might have seen this as the difference of squares in the past. But I think it's actually a little bit simpler just to think of this as a special case of the previous things that we were looking at. Now you just go ahead and factor this, or we just factored it. Now you actually employ the zero product property I meant to say. So you make your two mini equations. One is x plus 3 is equal to 0, and the other one is x minus 3 is equal to 0. Then you have just one-step equations. We undo adding 3 by subtracting 3. So x is equal to negative 3. We undo subtracting 3 by adding 3. So x is equal to positive 3. So those are our two solutions for x. Go ahead and try this next one yourself, thinking about how this is just a special case of what we've already been looking at. Welcome back. Let's go ahead and identify our b and c here. So we can rewrite this one as really x squared plus no x's minus 121 is equal to 0. That means b is 0, c is negative 121. What multiplies to negative 121 and adds to 0? That would be negative 11 and positive 11. Now we can just set up our two mini equations. So we either have that x minus 11 is equal to 0, or x plus 11 is equal to 0. We undo subtracting 11 by adding 11. Negative 11 plus 11 makes 0, so x is equal to 11. We undo adding 11 by subtracting 11. 11 minus 11 makes 0, so x is equal to negative 11. And those are our two solutions for x. Now note that if I have anything in front of the x squared, I can't quite do exactly what I've been doing. So if you just have an x squared by itself, great, you come up with your two numbers and jump straight to the parentheses. Here we ask ourselves a similar first question, but then we have another step in between. So instead of just asking ourselves what multiplies to c, we're going to ask ourselves what multiplies to a times c. Now that is secretly what we were doing before, because if I just have x squared plus bx plus c is 0, well then a is equal to 1. So asking yourself what multiplies to 1 times c is identical to asking yourself what multiplies to a times c. But here we're going to very explicitly have that step. You still then ask yourself what's going to multiply to ac but add to b. However, instead of jumping straight to the parentheses, you have to do these middle factoring by grouping steps, where we're going to rewrite the middle term in terms of these two numbers we just came up with. And this will make a little bit more sense with a concrete example. So let's take a look at that. Now, first of all, for this very, very first one, there's two different ways we can go about it. We could do the long way, which I'm about to show you here. Or if you actually already notice, hey, I know a number that goes into 2, 22, and 20, go ahead and factor that out first before you do the longer way of factoring, because what goes into 2, 22, and 20 in terms of factors? The 2 does. So you can pull out a 2, and by that I mean take a 2 out and basically undo distribution. So what you're really then doing is taking all of these middle terms and dividing them by 2. If you notice, I haven't actually changed the value of the problem. I theoretically could distribute this 2 back in, and I would be left with the original. So I have 2 multiplied by 2x squared divided by 2 is x squared. 22x divided by 2 is 11x. 20 divided by 2 is 10. Now, a lot of folks will jump from this first step to the second step. I'm just showing this middle step for pedagogical purposes, that when you pull a 2 out, that means from all 3 of these other terms, you need to divide out the 2. That's what it means to pull out the 2. If I were to redistribute the 2, I would have the original. Now, what's left here in the parentheses looks exactly like what we were just working with. So you ask yourself, here if b is 11 and c is 10, what's going to multiply to 10 but add to 11? That would be 10 and 1. So we would have 2 times x plus 10 times x plus 1 is equal to 0. And then we just solve our 2 mini equations. So we have x plus 10 is equal to 0, or x plus 1 is equal to 0. Subtract 10, subtract 10, subtract 1, subtract 1. Cancels out to make 0. X is equal to negative 10. Cancel out to make 0, x is equal to negative 1. That is always relevant if that leading coefficient is actually something you can divide everybody by. But let's say it wasn't. Let's say you have more of a situation that you have over here, where I'm like, okay, does anything go into 4x squared, 15x, and 9? Unfortunately, no, because 15 and 9, 3 goes in, but 3 doesn't go into 4, and 4, 2 goes in, but 2 doesn't go into 15 or 9, so it can't do that. So now, instead of identifying b and c, I'm going to identify b and a times c. So b in this case is 15, still that middle term, but now a times c is 4 times 9, which is 36. So you're trying to ask yourself what will multiply to 36 but add to 15. And if you're not sure, just start listing some factors of 36. So we have 1 and 36, we have 2 and 18, we have 3 and 12. Oh, that looks good. 3 plus 12 is 15. So if in doubt, just start listing them out. And remember, if it's a positive, you either could have a positive times a positive or a negative times a negative. Since b is positive, we knew we wanted to go with the positive terms. Now, don't just jump straight to the parentheses here. We can't do that this time. Instead, we're going to rewrite the middle term in terms of these numbers we just came up with. So this is 4x squared plus 3x plus 12x plus 9 is 0. We just rewrote that middle term in terms of those other 2 terms. I'm going to change color here for clarity. Now, you might ask yourself, what if I wrote 12x and then 3x? The beauty of mathematics is it actually doesn't matter which order you wrote it in. Just split the middle term into those 2 terms. I haven't changed the value of the problem. 3x plus 12x does give me 15x. I've just rewritten it. Now this is where the grouping comes in. So you're going to make 2 groups, and you're going to ask yourself, what is the greatest common factor of this group? So what's the biggest thing that multiplies into both 4x squared and 3x? That would actually just be a plain x. So now I'm going to pull out a plain x. I'm left with 4x squared plus 3x, each of them divided by x. Just like I pulled out a greatest common factor over here, I can pull it out over here. Plus, and then we've got, for 12x and 9, what's their greatest common factor? That would be 3. So I'm going to pull out a 3. Just for the sake of clarity, I'm going to erase some of this sort of guesstimating our magic numbers over here, just so we have a little bit more room to write. We already know that the numbers we came up with were 3 and 12. So now when I pull out a 3 here, I again don't want to change the value of my problem, so I'm going to be dividing each of these terms by 3. And now I'm going to actually simplify this. This kind of middle step is me just showing my thinking. A lot of people would then jump straight from identifying the greatest common factor is x so that I can rewrite 4x squared plus 3x as x times 4x. 4x squared divided by x leaves me with 4x, plus 3x divided by x is 3. Similarly, we have here that 12x divided by 3 leaves me with 4x, and 9 divided by 3 leaves me with 3. So a lot of times people will jump straight from here to here. I'm again just showing what you're actually doing in between. If I were to redistribute this out, I would be back to the original. Now the reason why we just came up with the numbers that we did, and if we did this right, is these two parentheses are now identical. So what we're now technically doing is we're factoring out a 4x plus 3 from each of these terms. And then in the next parenthesis, well, x times 4x plus 3 divided by 4x plus 3 leaves me with x. 3 times 4x plus 3 divided by 4x plus 3 leaves me with 3. A lot of times the way that people sort of remember a short way of doing this is you have one parenthesis of what's the same. In this case, 4x plus 3 is what they had in common. And then you have another parenthesis of what is different. In this case, the x and the 3 were the two terms that were different. Still equal to 0. And then, of course, don't do all this work and then forget that last step. The reason why we did this is we can now employ the zero product property. So we can say our two many equations are that 4x plus 3 is equal to 0, or x plus 3 is equal to 0. I'm going to solve the easier one first. The only thing I need to undo with x plus 3 is adding 3. I undo that by subtracting 3. So x is equal to negative 3. For 4x plus 3 is equal to 0, that's two steps, but I can still do it. First I want to undo adding 3 by subtracting 3. Then 4x is equal to negative 3. Then I want to undo multiplying by 4 by dividing by 4. So x is equal to negative 3/4 as my other solution. And both of those are solutions to this equation. Notice that our final factored form here was not the same as the two numbers I came up with, 3 and 12. They actually don't directly appear, well, 3 technically does, but 12 doesn't directly appear here. So you have to do these middle steps first of split the middle term into the two terms you just came up with, those two numbers. Then from the first group, pull out its greatest common factor. From the second group, pull out its greatest common factor. If you did that right, you can rewrite this as one parenthesis of what's the same and one parenthesis of what's different. I want you to pause the video and go ahead and try this next one yourself before I go over it. Welcome back. Let's go ahead and go over how to factor this. So first we want to ask ourselves, is there something I can pull out from all three terms? 12, 11, and 2 unfortunately don't have any factors in common. So I'm going to identify B, and I'm going to identify A times C. B is 11. A times C is 12 times 2, gives me 24. What's going to multiply to 24 but add to 11? That would be 8 and 3. And since my leading coefficient is not 1, I need to split this middle term into those two terms I just came up with. So then I have 11x being broken into 8x plus 3x, or the other way around, doesn't matter which order you write it. And then I'm just going to drop down everything else. So that's a 12x squared, that's a 2, and we have equals 0. Now that I've identified those, I want to make my two groups. So you group the first ones, and you group the second ones. In the first group, you ask yourself, what is their greatest common factor? In this case, it's not just an x, but it's actually a 4x, because 4 goes into 12 and 8, and x goes into x squared and x. So I pull out a 4x, and what's left here in parentheses is 12x squared divided by 4x, leaves me with 3x. 8x divided by 4x leaves me with 2. Then I want to ask myself the same things for this next guy. And what's the greatest common factor that goes into 3x and 2? Well, there's actually not really one, but 1 goes into everybody. So its greatest common factor is actually just 1. And 3x divided by 1 is still 3x, and 2 divided by 1 is still 2. Now we're in business because I have the same parentheses here. So I make one parenthesis of what's the same, which is 3x plus 2. What I'm technically doing is dividing 3x plus 2 out from both of these terms. And one parenthesis of what's different, 4x plus 1. Or I should have said that I'm technically factoring it out. So I factor it out by dividing this term by 3x plus 2. That leaves me with 4x. I'm factoring out 3x plus 2 from this term by dividing by 3x plus 2, which leaves me with 1. Now this is ready to set up our two mini equations. So we have one that's 3x plus 2 is equal to 0, and we have another one that's 4x plus 1 is equal to 0. I want to get x by itself by first undoing any addition subtraction. So here I undo adding 2 by subtracting 2 from both sides. So I'm left with 3x is equal to negative 2. Then I undo multiplying by 3 by dividing by 3 on both sides. So I'm left with x is equal to negative 2/3. Same idea for the other one. So I want to again get x by itself. So I first undo adding 1 by subtracting 1 on both sides. I'm left with 4x is equal to negative 1. Then I undo multiplying by 4 by dividing by 4 on both sides. So I'm left with x is equal to negative 1/4. Now for this next one, you might be like at first, well, this is not a quadratic, and it's not. However, I can make it look like one, because is there a greatest common factor between all three of these terms? There is. There is an x, and actually to make my life even easier, I'm going to specifically pull out a negative x because I noticed that my leading term is negative. So if I pull out a negative x, if I factor out a negative x, that means for these remaining terms, I want to divide each of them by negative x. This is sort of an optional middle step I'm showing. So negative 3x cubed divided by negative x leaves me with 3x squared. Negative 5x squared divided by negative x leaves me with a positive 5x. Negative 2x divided by x leaves me with a positive 2. And now I'm ready to factor this remaining part. I want you to pause the video actually and go ahead and try to factor this remaining part yourself. Welcome back. Let's identify what b and a times c are. So b in this case is 5. That is the term with the plain x. And then a times c is 3 times 2, which is 6. So what's going to multiply to 6 but add to 5? In this case, that would be 2 and 3, because now we're wanting to just keep everybody positive because we have a positive 6 and a positive 5. So we're going to split this middle term into those two terms we just came up with. Again, doesn't matter which order you write it. So that becomes 3x plus 2x and drop down everything else. All I did to change from this step to this step was I split the 5x into 3x and 2x. If I were to work backwards again, 3x plus 2x is 5x. I haven't changed the value of my problem. But now I'm ready to go with my grouping. So here is my first group. So between 3x squared and 3x, what is their greatest common factor? That would be 3x. So I'm left with 3x. I'm going to kind of do a big parenthesis here because I'm about to have multiple parentheses floating around because I'm really just dropping down this negative x and not touching him the whole time. 3x in parentheses because I'm pulling out 3x from this group. 3x squared divided by 3x, it leaves me with a single x. 3x divided by 3x leaves me with 1. Be careful that if you're thinking that cancels out to make 1 because you're actually doing 3x divided by 3x. Same thing with this next group. You ask yourself its greatest common factor between 2x and 2. That would be 2. So I want to pull out a 2 from them. 2x divided by 2 leaves me with x. 2 divided by 2 leaves me with 1. And now for this middle term, I now have a x plus 1 that they have in common. So I can rewrite this as one parenthesis of what's the same, x plus 1, and one parenthesis of what's different, the 3x plus 2. Now when it comes to the zero product property, I've actually got three equations going on. I've got one, actually I should not use red again. I've got one that's just negative x is equal to 0. I've got another one that's x plus 1 is equal to 0. And I've got another one that's 3x plus 2 is equal to 0. All three of those are equations I need to worry about. If I have negative x is equal to 0, well, I technically divide both sides by negative 1 because that's really what x is being multiplied by, but 0 divided by anything is still just 0. So I just have x is equal to 0. For x plus 1 is equal to 0, I undo adding 1 by subtracting. So x is equal to negative 1. And then for my last one, that's two steps. I undo adding 2 by subtracting 2. 3x is equal to negative 2. And then I undo multiplying by 3 by dividing by 3. So x is equal to negative 2/3 is my final answer. And all three of those are solutions. Of course, not everything is factorable, and sometimes there are other techniques we have to use instead. The zero product property is also a really nice technique to use. So we use factoring whenever we have things that are like x squared plus a bx plus c, with b and c just being some numbers equal to 0, or some way I can manipulate it to look this way. And if it's specifically like this, then I just have to ask myself what multiplies a c and add to b and jump straight to the parentheses. If there's something still in front of the x squared, then I have to do the formal factoring by grouping we were just looking at. And either way, I get some parentheses to use the zero product property with, and I'm good. For the square root property, I don't actually set it equal to 0. If I just have x squared equals some number, or some way I can re-manipulate it to look that way, then I can just use the fact that if I know that x squared is equal to something, then x better be plus or minus the square root of that something. So if, for example, I have x squared is equal to 1, square root, plus or minus, I know then that x better be either positive 1 or negative 1. That's what that plus or minus 1 means, and it might be worth explicitly listing as two separate solutions. So let's take a look at an example of that. So first of all, before we employ the square root property, we should make this look like x squared equals a number. So we want to basically get x squared by itself. I can only employ the square root property if it's even possible for me to get x squared by itself. As soon as you throw in a plain x, you can no longer use this property. But here we're good. We have no plain x's. So here, to get x squared by itself, well, how do I undo subtracting 9? I just add 9 to both sides. So I'm left with x squared is equal to positive 9. Then the opposite of squaring is square rooting. And when I use that square root, I need to use plus or minus that square root, since a negative times a negative is also a positive. So I'm left with x is the positive square root of 9, or the negative square root of 9. And what is the square root of 9? That would be 3. So x is equal to plus or minus 3. And that's exactly the same answer that we found whenever we formally factored it. Go ahead and try this next one using the square root property as well. So for this one, we're going to add 121 to both sides to undo subtracting 121. Then x squared is equal to 121. Now that x squared is by itself, we're good. We can square root both sides, and we want to make sure to include that plus or minus when we square root. So x is equal to the positive root of 121 or the negative root of 121. So x is equal to positive 11 or negative 11. Had the square root of 121 not been a nice clean number, or we could have just left it as is if it didn't simplify anymore. These are more complicated examples where we can actually use the same thing. So we just have a something squared term, and as long as there's just like a something squared term that I can get by itself, I'm allowed to use the square root property. So for this first one, I want to ask myself, how do I get this x squared by itself? Same steps as how you normally get x by itself. So I undo addition, subtraction first. So I undo adding 1 by subtracting 1 on both sides. I'm left with 4x squared is equal to 6. Then I still have this 4 hanging out front, and I don't want him. So I undo multiplying by 4 by dividing both sides by 4. So I'm left with x squared is equal to 6 over 4. And even though normally I would say you should probably simplify your fraction, I'm actually going to encourage you not to until the end, because now I undo this with a plus or minus square root. So x is equal to the positive square root of 6 over 4 and the negative square root of 6 over 4. And that square root can be rewritten as the square root of 6 over the square root of 4. And one of those is a perfect square, specifically 4. So this is actually positive square root of 6 over 2, since the square root of 4 is 2, and the negative square root of 6 over 2, since the square root of 4 is 2. And those are your two solutions for x. This next one, it might be tempting to go ahead and FOIL out this x minus 4 squared, which would technically lead you to the right answer eventually, but there's a nicer way to solve this. And as tempting as it is to distribute this 3 inside this, you don't want to do that, because technically this is 3 times x minus 4 times x minus 4. And if you distribute the 3 in, then I have a 3x minus 12 times an x minus 4. I no longer have a thing squared. That would be an alternative way to keep expanding it out in order to solve this guy, but it's actually not the nicest way to solve it. I encourage you not to do that. Instead, treat that whole x minus 4 squared like it's a variable. So if I just have 3 times some variable equals 15, how do I get that funky variable by itself? Well, I undo multiplication with division. Again, distributing the entire thing out and doing it properly is not technically wrong. It's just more work than you need to do if you notice you just have a thing squared somewhere. So 3 divided by 3 makes 1. X minus 4 all squared is equal to 15 divided by 3 is 5. And now I can still undo that square with the square root property. So I square root both sides, plus or minus on that square root of 5. So that leaves me with x minus 4 is equal to the positive square root of 5 and the negative square root of 5. And because there's more than just an x over here, what I really just figured out were 2 equations. And actually, let me write that a little bit nicer to emphasize that. So we have x minus 4 is equal to plus or minus root 5. So I'm going to split that into, that means x minus 4 is equal to the positive square root of 5, or x minus 4 is equal to the negative square root of 5. Then for both of these, what would be my final step to get x by itself? Well, you would add 4 to both sides. So you would have x is equal to the square root of 5 plus 4, or x is equal to the negative square root of 5 plus 4. And those would be your 2 solutions. Square root of 5 does not simplify further, so you would just write that as is. If you cannot factor it, if you try asking yourself a times c, what's going to multiply to a times c and add to b, and you can't think of anything, and you can't do the square root property because I don't have a something squared I can get by itself, what you can always use is the quadratic formula. That will work without fail for every single quadratic equation. The way that works is x is the opposite of b, plus or minus the square root b squared minus 4ac all over 2a. And that's exactly how you're going to plug it in. So let's go ahead and do that. Before you start plugging in, I highly recommend you just carefully label exactly what a, b, and c are. So in this case, a is secretly 1, b is 5, and c is 1. Now, if I wasn't told to solve using the quadratic formula, I might first see if this guy can factor. If there's anything that multiplies to 1 and adds to 5, there's not. I also can't use the square root property because of this 5x as well. There's no way to get that x squared by itself. Now I'm ready to use the quadratic formula. So I'm going to rewrite the quadratic formula in general first, then I will plug things in. So x is the opposite of b, plus or minus the square root b squared minus 4ac all over 2a. So opposite of b, negative 5, plus or minus the square root of 5 squared minus 4 times 1 times 1, ac, all over 2 times 1, 2 times a. Now when it comes to simplifying this, you want to think in terms of order of operations. This square root is sort of like a parenthesis, so you want to tackle what's inside him first. And in terms of what's inside him, I want to do that 5 squared first, 25. And then we have the 4 times 1, which is just 4. All divided by 2 times 1 gets me 2. Then I want to continue to simplify underneath the square root, so 25 minus 4 gets me 21. And then you want to ask yourself, does the square root of 21 simplify further? Well, 7 and 3 go into 21, and neither of those are perfect squares, so it does not. And this would simply be your final answer. And keep in mind, those are literally 2 separate numbers. One is negative 5 plus the square root of 21 over 2. And the other one is negative 5 minus the square root of 21 over 2. Those are 2 different answers. That's what that plus minus means, is these are 2 different numbers. All right, I want you to pause this video and go ahead and try to solve this one yourself using the quadratic equation. All right, welcome back. For this one, you may have also noticed that maybe we didn't need the quadratic equation, because if you notice, 9 times negative 2 is negative 18. And then if you ask yourself what multiplies negative 18 and adds to 3, well, 6 and 3 actually works if you make the 6 positive and the 3 negative. But let's say you didn't think of that and you want to use quadratic formula anyway. Quadratic formula will always work. So in this case, A is 9, B is 3, and C is negative 2. And then you want to plug it in. So x is opposite of b, plus or minus the square root, b squared minus 4ac all over 2a. I should have written that in general too. So opposite of b plus or minus the square root, b squared minus 4ac all over 2a. And the faster you memorize that formula, the easier your life will be. The formula is never going away. Now, in terms of simplifying, we want to tackle that square root first, and specifically we want to do the exponent separate. So 3 squared gets me 9. Then I want to multiply these three numbers. So we have negative 4 times positive 9. That gets me a negative 36. Negative 36 times a negative 2 makes that a positive 72. All over 2 times 9 is 18. Then we want to keep on going. So negative 3 plus or minus 9 plus 72 gets me 81 all over 18. And hopefully you recognize the square root of 81 is actually a number I know. That is 9 all over 18. There's a couple different ways you could approach the simplification from here. If you're going to do it by just pulling out a greatest common factor, which I will show you since that's what a lot of folks do, you want to ask yourself, what is the largest number that goes into negative 3, 9, and 18? That would be 3. So you could divide all three numbers by 3. Negative 3 divided by 3 leaves me with negative 1. Plus or minus 9 divided by 3 leaves me with 3. 18 divided by 3 leaves me with 6. Note that, like, had that 9 had a square root of 2 or something like that attached, if you divided by 3, you would just be dividing that outside 9 by 3. Whatever is really underneath the square root still, just treat it like it's sort of like an x or like some type of term. But that's really just an aside. Now from here, the way I like to continue to simplify it is to split this up into what the plus version is and what the minus version is. You also could have done that from this initial step if you didn't like dividing all three terms by 3. So one of these terms is negative 1 plus 3 over 6, and the other one is negative 1 minus 3 over 6. Negative 1 plus 3 gets me positive 2, and 2 goes into both of those terms. So 2 divided by 2 leaves me with 1, 6 divided by 2 leaves me with 3. One of my answers is 1/3. Negative 1 minus 3 is negative 4 over 6. In this case, again, 2 goes into both of those, so I can divide both by 2. Negative 4 divided by 2 leaves me with negative 2. 6 divided by 2 leaves me with 3. So positive 1/3 and negative 2/3 are my two answers. There are also problems that aren't technically quadratic, but that we could think of as quadratic. The way that you recognize that is if this middle term's exponent times 2 gives you the first exponent, then it can be rewritten in quadratic form, because I could think of x to the 4th as x squared all squared. And now I have a middle term and I have something else squared. The way that we do this more explicitly is, first, again, you recognize that it could be rewritten in quadratic form if that first term's exponent is twice that of the middle term. And if that's the case, we go ahead and rewrite this with this u substitution, as we call it. The reason why we pick a u is because u substitution is also something in calculus, which follows like a very similar step, and it kind of gets you used to substituting things with a u. You can pick whatever variable you want, though. So in this case, if I make u x squared, that means u squared is x squared squared, which is x to the fourth, and I could rewrite this as u squared minus 5 times u plus 4 is 0 by replacing x squared with u and replacing x to the fourth with u squared. And then this looks like something that's quadratic. Similarly here, this next one is a good candidate because 3 times 2 does give me 6. So if I called u x to the third, that makes u squared x to the third squared, which means I'm literally multiplying x to the third by itself twice. So 3x's times 3 more x's gives me x to the sixth. So I can rewrite this as u squared again plus 7 times u minus 8 is 0. Some people skip this rewriting by u step, but this helps you kind of keep this systematically as quadratic. And that's exactly what this is telling you to use. Use like that replacement u, solve everything in terms of u, and then at the end, re-replace what u is. So let's look at this as an example. So first of all, we know that it is a candidate because 2 times 2 does get me 4. That u term will always be your middle term. So in this case, that's x squared. We want to double check that means u squared gets me what I expect. So if I take x squared and then square it, x squared times itself, that's 2x's times 2 more x's, gives me x to the fourth. So I can rewrite this in terms of u as 3x, I just said in terms of u, and then I start right down x's again. My bad. So x to the fourth is the same thing as u squared, so 3u squared minus 2x squared is the same thing as u, minus 1 is 0. Now I just want to treat this like a regular old quadratic, so I ask myself what multiplies to a times c, but adds to b. A times c is 3 times negative 1 is negative 3, b is negative 2. So what's going to multiply to negative 3 but add to negative 2? That would be negative 3 and positive 1. So I'm going to rewrite that middle term as negative 3u plus u and drop down everything else. Haven't changed the value of my problem. Then I'm just going to keep on factoring as normal. So I'm going to group these between 3u squared and negative 3u. Their greatest common factor is 3u. So I'm going to pull out a 3u. 3u squared divided by 3u leaves me with u. Negative 3u divided by 3u leaves me with negative 1. Between u squared and negative 1, their greatest common factor is simply just 1. So u divided by 1 leaves me with u. Negative 1 divided by 1 leaves me with negative 1. Now these have one parenthesis of what's the same, and they have something that's different, but they should have the same thing in parentheses. So I am now technically factoring out a u minus 1. And if I do that for the first term, what's different is the 3u. That's what's left whenever I divide out a u minus 1. For the second one, what's different is a 1. That's what's left when I divide out a u minus 1. Now I am ready to go ahead and set up my two mini equations. So one of them is u minus 1 is equal to 0. Another one is 3u plus 1 is equal to 0. I want to get u by itself and then substitute in what u is. So I add 1 to both sides. I get u is equal to 1 for the first one. For the second one, I want to undo adding 1 first, so I subtract 1 on both sides. 3u is equal to negative 1. Then I want to undo multiplying by 3, so I divide by 3 on both sides. U is equal to negative 1/3. However, I am not done yet. What I just solved for was in terms of u. Remember, u meant something in terms of x squared, so I need to re-replace that in. What is u equal to? U is equal to x squared. So I actually have, in this first case, let me write with a little more room, if u is equal to 1, that means since u is x squared is equal to 1. And now this looks like something that's good game for the square root property, because I just have an x squared equals a number. So I'm going to square root both sides, and what do I need to remember when I undo a square with a square root? Plus or minus. So x is equal to plus or minus the square root of 1, which really just means x is equal to plus or minus 1, positive 1 and negative 1. I want to do the same thing here. So I replace u with an x squared equals negative 1/3. Now if I undo with a square root, what's the issue? I can't have a negative underneath the square root. There are no real solutions that come from that part of the equation. I really just have x is equal to plus or minus 1. This next one is a very similar candidate because I could expand this all out, but that would be the hard way of solving this problem. I want to do it the smarter way. So here, I still have stuff squared and that same stuff here in the middle. So let's try making u equal to x plus 2. If that's the case, then u squared is equal to x plus 2 all squared. And that's exactly what I can do. So this first thing of the whole thing, x plus 2 squared, that's equal to u squared. 11 times this parentheses x plus 2, well, that's just 11u. And then you drop down everything else. Now you factor in terms of u. So here there's no leading coefficient in front of the u squared. That's super nice. That makes my factoring a little bit simpler. So I just need to ask myself what multiplies to negative 12 and adds to 11. Secretly the same question as 1 times negative 12. Because c is negative 12, b is positive 11. So what's going to multiply negative 12 but add to positive 11? Well, that would be positive 12 and negative 1. I could formally do the by grouping if I forgot this was a special case and I would get the same answer, but here I actually can just jump straight to the parentheses because there's no leading coefficient in front of the u squared. Now I want to actually solve my equation, so I have that u plus 12 is equal to 0, and we have u minus 1 is equal to 0. I undo adding 12 by subtracting 12. U is equal to negative 12. I undo subtracting 1 by adding 1. U is equal to positive 1. But then I want to remember that I want things in terms of x, not u. U is equal to x plus 2. So I replace u with what it was again. So x plus 2 is equal to negative 12. X plus 2 is equal to 1. And now both of these have one more step to get x by itself. I undo adding 2 by subtracting 2. So x is equal to negative 14, or x is equal to negative 1 as my final answers. And that's a lot less work than expanding this whole thing out. If you want even more examples, your textbook has lots of examples, and I also encourage you to reach out to your instructor. Hopefully you found these useful.